Okay, good morning, everyone. Welcome back to the Rediscovering the Space, this cycle of inspirational speeches we have organized in the framework of the PhD program in Aerospace Science and Engineering here at Politecnico di Bari. I give the word to our rector, Francesco Cupertino, that will introduce today's talk. Please, Francesco.
Thank you, Marco. This afternoon, I would like just to welcome our new guest to this new speech inside our cycle of meetings. Is with a particular emotion. This afternoon, I'm welcoming people who are following a very important mission, not just for science, but maybe also for the future of human beings. I would like to share with you tonight an experience that I had a couple of years ago. I had the opportunity of visiting in Seattle people working for SpaceX, and when we were talking, we started talking about their motivation. You know, when you go there and you talk with somebody who is working on a mission to explore another planet, you ask what is motivating you in something so challenging, and the answer I got was that their motivation was mainly to give human beings another opportunity in case our planet Earth will be no more good for human beings to live in our planet. So give humanity a second chance. I think that it is one of the most inspirational objectives that we could have in our professional experience. And tonight we are giving to our students in our PhD in aerospace engineering and science that again I remember is something, is an initiative that we started this year together with the University of Bari in order to give to our region the perspective of having a PhD course on a topic that is of great interest, not just scientific interest, but is of interest for the developing of new companies and initiatives and research in this field in our region. And it will be for me very interesting to stay here with you and listen some new information about this new mission of exploration of planet Mars that probably will give us more insight and more information about the possibility of having in the next future really a stable place where to live for the first time for the human beings on another planet. So I will give back the floor to Marco De Tullio for the introduction of the colleagues who will talk to us this afternoon on their work on the Mars mission of the Perseverance. Is this correct? The pronunciation of the rovers. So Marco, please introduce our guests.
Okay, thank you, Francesco. As almost everybody knows now, after a lot of talks, we planned a talk about every 2 weeks, but today we have an unscheduled event. So let me say a special event. We have the chance to listen and interact with some of the Italians who work at NASA Jet Propulsion Laboratory, the JPL. And this was an opportunity that we could not miss. So I'm really happy for that. In particular, our guests have played critical roles in the design, simulation, test, and operation of the robotic systems for the Mars 2020 missions. I'm sure that almost all of us were glued on the TV on the 18th of February when NASA's Perseverance rover touched down safely in the Jezero crater on Mars. It was a memorable event, starting a new era of exploration, and you know, rocks will be collected and returned to Earth for the first time, and that's amazing. So I really thanks Alessandra Gushikyo, that now is our PhD student and was already and is already an engineer at NASA JPL. And thanks to him, we managed to have here Dr. Cinzia Zuffada, Alessandro Gushikyo, Paulo Belluta, and Stefano Capucci, who I really thank for their availability. They will give us an overview of different opportunities for Italian students to join research program in the US, but also at JPL. And then they will go into details of several technical and engineering aspects of Perseverance rover, but also on the Mars helicopter Ingenuity. But also, Paulo will explain us how to move a vehicle on another planet. That is something so strange, where interactive communication is not possible. So I'm sure that we will spend very nicely the next hour and more. Just let me conclude by reminding you to ask questions at the end of all the presentations. And please ask to the chat, on the chat, the permission to talk, and I will give you the permission to make questions to our guests. So finally, since I like to involve colleagues in this seminar, it's time to give the word to Maria Cinefra, Professor of Aerospace Structure and Design here at Politecnico of Bari, and she will introduce the speaker, give some details about their role at JPL and their CVs. So she will moderate the events. Thank you. Maria.
Thank you, Marco. Good evening to everyone. So I just want to spend a few words before presenting the speakers, because it is a great pleasure for me to introduce this seminar, because a few years ago I had the opportunity to visit JPL. I was in Pasadena for a visiting period at California Institute of Technologies. That is joined with JPL, and during this visit I have to say I had a meaningful experience, because it was the first time for me in a NASA laboratory, and that visit gave me a lot of motivation for my research. So I thought that every researcher or student in the aerospace field should have this kind of experience. So when I met Alessandro Gushikyo for the first time there in Pasadena, he's Apulian as me, we discussed about the possibility to create a channel for the Apulian students to the JPL in order to give them the possibility to get this direct experience with the NASA reality. And I hope that this seminar is the first step towards this objective. So now I present the speakers. First of all, Cinzia Zuffada, that she is graduated at the University of Pavia in electronic engineering, and currently she is Associate Chief Scientist and President of Italian Scientists and Scholars in North America Foundations. And she will give us a summary of research opportunities for Italian students in the US and at JPL. The second speaker is Alessandro Gushikyo. He's graduated both in Politecnico di Bari for bachelor degree and Politecnico di Torino, Politecnico of Turin for master degree in mechatronics, and he's currently PhD student at Politecnico di Bari. And he's involved in different flight missions, but today he will give us he will explain his contribution to the test campaign for Perseverance rover. Then Paulo Belluta, he will speak about his extensive experience in driving Mars rovers over difficult terrain, and he played a key role in different missions. And finally, Stefano Capucci. He is graduated in Politecnico di Torino in aerospace engineering, and he is the thermal system lead for Mars helicopter mission, and he will discuss about his role, his experience. So I give the floor to the speakers. First of all, Cinzia. Thank you.
Thank you, Professor Cinefra. Thank you to the organizers, Direttore, for being here and welcome us. And thanks to my colleagues for thinking of me to participate to this wonderful event. Let me start with sharing my presentation. Now this unfortunately, it does not give me the opportunity to select what I want to share.
Cinzia, we see your PowerPoint.
Yeah, but it does not give me the opportunity to select which one I want, right? Do you see the PowerPoint that I prepared for the presentation?
No, we see the blank PowerPoint, the blank presentation.
Okay, let me try one more time. Do you see it now?
Yes, yes, yes.
Thank you so much. Sorry for these technical difficulties. So I'm actually talking to you with two hats here as a JPLer, the Associate Chief Scientist of the laboratory, but also as the President of ISSNAF, because I want to tell you about opportunities that might be open to students at your university or new graduates, even beyond the JPL, right? But I want to start with JPL. And so JPL is part of NASA, but it's also part of Caltech. It's a federally funded research and development center, which means that NASA has a long-term investment in this laboratory. It goes back to the beginning of NASA in 1958. But it's operated by a university, so we are part of Caltech. It has more than 6,000 employees. At the moment, only a little over 1,000 are allowed to be at JPL to work on projects that required physical presence in the laboratory. Most of us have been working remotely for the past year now. And we have about $2.5 billion year revenues, which really is the money that is made available through competitive process or through assignments from NASA directly to work with the goal of exploration, particularly the solar system exploration. So JPL started, of course, long before NASA existed, and it started as a laboratory, so to speak, in the boonies, close to the mountains, for Caltech students to do what would have been laboratory experiments in early rocketry as part of contracts that Caltech had with the Army. And so at the time, the Army was doing the early work in what was then the propulsion, the early propulsion. Of course, the propulsion took off in the United States after the end of World War II because of inputs from Germany, right? Like it happened elsewhere. But that's really the history. So space exploration for scientific purposes started as a technology reutilization from the military. So NASA was created in '58. JPL had become a laboratory before the beginning of NASA, and it stayed independent but affiliated. And it has been a choice. It has been a choice all along to maintain this independence and be a division of Caltech. This is very important because Caltech provides also intellectual grounding and leadership to everything that we do. The first successful experiment that JPL did in space was the Explorer mission at the end of January of '58, which was the first scientific mission that the West had a few months after Sputnik. And from that, JPL has proceeded in the exploration of not just the solar system, with the Voyagers that a few years ago have left the solar system, as you all know. So we have man-made objects by JPL that are now in the interstellar space. And we don't do just robotics, although we are very proud, of course, of what we do in terms of robotics exploration. We are also a very important center for earth science, as well as astrophysics. And so I thought I would create this context because indeed the opportunities are very many. And I won't go into the wonderful stories in robotics because my colleagues will be able to do that a lot better than I can. Here I have a list of opportunities that JPL has opened to the community. So the JPL postdoctoral scholars programs, those are open to people from all over the world. And so we have opportunities that are there all the time. I recommend for somebody who is interested to sort of familiarize yourselves with the sites that we have and the description of the opportunities. Because if maybe you are not ready now, but you can look at what is possible once you get your doctorate. The same thing is true for the NASA postdoctoral program. And the NASA postdoctoral program is open, again, to young doctors all over the world. And it's open to all the NASA centers. So this goes beyond opportunities at JPL. So in general, we are looking for candidates who are within 5 years from their PhD. And it's up to 3 years postdoctoral opportunity. Now, for foreign students that are at foreign institutions, such as yourselves, JPL has something that is called the JPL Visiting Student Research Program. And both Stefano and Alessandro have utilized this formalism when they spend time at JPL as students from Politecnico di Torino. So it does require an invitation. So there needs to be mentors who are interested in hosting students from other universities. So there is an opportunity for faculty here at the Politecnico of Bari to form some relationships. We have some wonderful people here today who will be ready to be mentors of students, you know, in a very short time. And so through personal grassroots level collaborations, you might have an opportunity to be an intern. Of course, right now, there are no interns at the laboratory, right? We are in this COVID situation, but let's look positively to the future, so there will be. And NASA also has a bunch of programs that are open to students from outside the United States. For those of you who enroll in American universities and are then foreign students at American universities, then there are additional opportunities that might be available, and they will depend on programs at the time. Now I want to quickly move and present my second hat, right? I have become president of an organization, a non-profit American organization that gathers the network of Italian scientists and scholars that work in North America. People like myself who have been educated in Italy, moved and worked in the United States. And we form a network that has the mission and the opportunity to connect, empower, and celebrate this community. So we want to work and offer a resource both to ourselves as a network all over the North American territory, as well as a way of helping the younger generation. So those that are newly arrived in North America, those like students from Italy who might be looking for an opportunity to have some educational experience. That's the distribution of this network. So this shows at a very high level where the Italian intellectual diaspora in North America is distributed. You can see that most of us are in life sciences. There are lots of MDs who graduated in Italy and have left and work in North America. But there is also a healthy component of people in engineering, such as ourselves. All right, so going back to the programs that we offer for young people, and this is all on our website, right? So you can go and find out for yourselves. We have a mentoring program, and we offer mentoring opportunities to people who are still in Italy. They might be looking for, well, what's out there for me? Maybe a year from now, 2 years from now. So we match them up with people from our community who might be able to advise them and sort of, you know, identify maybe paths that they can explore. So that's one opportunity. We also have fellowships. So these are not ISSNAF supported. We work with donors. We work with organizations, including Italian organizations, who make available fellowships, and we help administer the fellowships. So we help in that process of screening candidates and matching good candidates to mentors in North America who would be receiving them, hosting them, and providing them with an educational and cultural and life opportunity that might be very valuable for you know, the beginning of one's career. So with this, I am done, and I know that you are eager to hear from my colleagues, but here are some materials. These will be distributed for your reference. And then at the end, I'll be happy to take questions. Thank you.
Thanks a lot, Cinzia, for your talk. So, Maria, can Alessandro start his talk?
Of course.
Okay. So, Alessandro, go. Thank you. Thanks, Cinzia.
I need permission first, Marco. I need permission to share.
Alessandro, you should have them.
Yes, now I do.
Okay, perfect.
All right. Okay. Hi, everybody. I'm Alessandra Gushikyo. I'm a robotics electrical engineer at JPL. Today, we're going to be talking about basically the evolution of robotics exploration for Mars. So, since I gave a very great introduction about JPL, we have 7,000 people working here. And I define this place as a Disneyland for engineers. That's because the machines that have been built in this place are amazing, are definitely amazing. So let's go through some of the, basically what I call Rover Generations. So in 1997, we had Pathfinder. It was the first rover designed by NASA to drive on the red planet. It was kind of a tech demo, and NASA soon realized how important it was to explore Mars, not just from from above, but actually we had to be there. So then we had in 2004 Spirit and Opportunity. As you can see, the size of this robot grew by actually a lot. These robots were two twins, and they were powered by solar panels. And in 2012, we had Curiosity, which I think is kind of almost the state of the art for robotics exploration on Mars, is much bigger, and it is the first to use a nuclear reactor to power both the electronic and the instruments on board. And the latest one is Perseverance. It landed basically just a few weeks ago in February 18. It is very similar to the previous rover, but it has actually a lot new that brings on the table. So when we talk about this incredible machine, one of the questions is why do we need this machine, for example, to be autonomous? Like, why do we need to send machines over there? Well, first because it's far and it's very difficult to reach. But most important is always a question that I kind of give to the students, the young people, is like, can you joystick these robots on another planet? It's like in the movie where you have somebody actually joysticking them. And I'm sure that Paulo later on, he will actually give us a huge insight about that. But the short answer for that is no, we cannot actually joystick these robots. And the reason is because the communication delay basically plays a huge factor in this. So just to give an idea, the communication between, for example, Earth and a satellite is just a fraction of a second. When we're talking about the moon, the wavelengths, it takes something like 1 second. When we talk about Mars, a communication can take up to 20 minutes. So you can understand that it's not feasible to drive this machine kind of in real time. And that's why this machine, they need to be autonomous. And like Jupiter is like 1 hour, so it would be completely impossible to drive in there by joystick. So why Mars? Why NASA and even ESA? So why the whole world is looking at this planet? The main reason is because even though today it kind of looks dry and dead, and in particular this is the picture of the gazebo crater, where actually Perseverance just landed a few weeks ago. 3, 4, 5 billion ago, we think that the Mars planet was actually like our planet. We had water, we had a dense atmosphere. So understanding what happened to the Mars planet could help us to understand, how to basically take care of our planet, and to understand actually the life and the evolution on these planets. All right, so again, I say there's a huge interest for the scientific community to go on Mars, to study Mars. But realistically, how many entities, how many agencies have been able to actually land on Mars? Well, the statistics says that only 50% of the mission have been successful. And one of the main reasons is that there are, between the launch and the landing, there are so many steps that need to be achieved. And if only one of them goes basically in a bad way, the whole mission is over. So you can really consider that in order for your payload, for your rover, for your lander to be actually functional, it first needs to land. And in fact, at JPL, we call this last portion of the mission, so where basically the spacecraft is actually entering and descending to the atmosphere, actually doing the landing. We call it EDL. And JPL has created this amazing video about 2020s, where basically, the spacecraft has been flying for 8 months to get to Mars. It's a very long flight, even though we're going extremely fast. However, all this maneuver needs to happen in such a precise and autonomous way, because what we said before, the communication plays a huge role. So when you actually approach the red planet, the landing must happen in a completely autonomous fashion way. So you have seen the spacecraft has to enter the atmosphere with a very, very precise angle, because too little and it will burn, too much it will fly away. And then it needs to use a parachute to basically slow down the spacecraft, because again, Mars atmosphere is just 1% of the atmosphere on Earth. So we really need a lot of basically drag to slow down our robot. And then when we get closer to the surface, we use an amazing system. It's called basically the sky crane, where first we use rockets to slow down the spacecraft, and where we get about 10 meters far from the surface, since we don't want the dust to actually deposit too much on the rover, we use this amazing sky crane system to actually lift down the rover. And once finally the rover touches down the surface, all these wires are cut and the sky crane flies away, because we don't want it to basically crash on top of our lander. And so, I mean, again, you have seen this video. Actually, on YouTube there is a version with the audio, which is even more impressive. However, again, this is just a simulation, right, or an animation. And with Curiosity, we really didn't have any real footage of this landing, but Perseverance actually has given us the opportunity to see some of this animation in real time. So this is another video that I really like to show, where you actually now can see the parachute, for example, opening in real time. It's actually a real footage taken from the Perseverance rover during the landing. And I love this picture because the pattern on the parachute is actually saying, "They are mighty things." And here you can actually see how the spacecraft, the rover, is actually approaching the surface. You can see how much dust gets moved by the thrusters, and that's why we had to use the sky crane to basically safely land the rover on Mars. And again, these are called 7 minutes of terror, and that's because it's really a terror for us, because there's nothing we can do. The machine has to do everything autonomous, and that's why when we finally land, you can see the happiness from the engineers and the scientists at JPL, because again, a lot can go wrong, but NASA, so far so good, has been able to land successful, I think, all the latest 5 spacecraft. We know issues, so we're really proud of that. All right, and then, well, we finally land on the planet. We can now start getting this, amazing picture, doing amazing science. And however, Mars is not an easy place to drive around. I mean, again, Paulo Belluta will talk a lot about it, but you can see what we try to do on Mars, just to try to avoid as much as possible dangerous places. We always try to drive where it's flat, where there is the minimum amount of rocks, because of course we want to protect the spacecraft and try to basically be able to operate it as much as possible, as long as possible. All right, so let's see some difference. So as I said, Curiosity and Perseverance, from the outside, they almost look the same. They do have the same size, they do have the same weight. In terms of size, almost as big as a SUV. So this actually is a pretty big, it's pretty massive rover that we are sending on another planet. In terms of technology and science, well, NASA now is following this approach where we call this robot like laboratory on wheels. So that means that this rover, they don't only give us, an insight about the red planet, in terms of, pictures and amazing landscapes, but they also are packed with a lot of technology that allow us to basically understand this planet from far away. So in the case of Perseverance, we have a lot of new instruments. One of them, which is I would say very cool, is actually called MOXIE. MOXIE is basically an instrument which is a kind of a tech demo where his role is to try to produce oxygen starting from CO2. Because again, even though Mars' atmosphere is very thin, it has CO2. And we know we can extract this oxygen from the CO2. So during this mission, this instrument will, I don't know from intent, but it will collect oxygen. And this will be very, very important for the very, very far future when we are going to have humans on Mars, because we know that we humans, we need oxygen. So it's very important to understand if we can generate oxygen on the red planet. We also have a lot of other cool instruments. So for example, this is the first time we have the RIMPAX, which is basically a surface radar. The radar is actually pointing the ground, so it's considered like a ground penetration radar. And this is very important because it allows us to see something that we cannot see with our own eyes, with just the cameras on board. So it will go much deeper, and it will allow us to understand how the structure of the red planet looks like underneath. And the other one, which I think is very important, is also the SuperCam, because it's kind of like it's a very cool device which has a combination of a camera, a spectrometer, a laser, which allows the rover to basically look at the composition of the rocks to basically help us to understand if life is still present on the red planet. And then we have, of course, the robotic arm, which we're going to be talking about in the next few slides. But first, I think for me as an engineer, it's very important to talk about some of the improvements that this robot obtained. So let's talk about the wheels. So this actually is a picture of Curiosity. And if you can really see, there is something wrong going on with this wheel. And as actually I'm talking about this hole. So we discovered that one of the weak point of the previous generation of Curiosity was its wheels. These wheels, unfortunately, they tend to break due to, again, the weight of the robot and the terrain on Mars, which again is full of rocks, very sharp rocks that can damage the wheels. So at JPL, engineers have been kind of like tackle this problem in a way that's kind of very, very cool, in a way that they have been testing and testing and testing different shape, different thickness. And you can see in this video that, they have actually came out with several designs, and they've been testing this design in a Mars yard. And you can see that thanks to this test, they've been able to now make the wheel much more reliable. So I'm sure that Perseverance will be able to drive very, very far away thanks to the improved wheels. Now, as I said, one of the most important payloads of this new rover is called the SCS. It's Sampling and Caching System. So with Curiosity, the goal was mainly, again, to have a laboratory on wheel. But the issue with that is that you cannot really study something if you don't already have the instrument for doing what you're looking for. So SES is a very, very challenging mission where the goal is to now not just do local analysis on Mars, but to actually be able to bring samples back to Earth. Because of course on Earth we have the best laboratories you can ever imagine. So if we can get these samples on Earth, then we can do tests that we didn't even know about before. So how does SCF work? Well, SCF is a very complex machine, is a very complex mechanism. Definitely fascinated from my perspective as a mechatronic engineering, because it's actually made of two robotic arms. The first one is the big one, the one that holds the turret, and that's actually the one that probably everyone is almost familiar with, where you have the rover with this big robotic arm drilling the red planet and taking samples. However, now JPL basically packed a second robotic arm, a small one, which is kind of like inside the rover. You can see here on the right. And what it does is actually taking the sample and putting the sample into a tube. And we hope that in the entire mission of Perseverance, we should be able to collect something like 20 samples with the hope to be able to return them to Earth. So this is Perseverance. However, Perseverance now is just one piece of a very, very, very complex mission that's Mars Sample Return. It's a huge mission that has now finally the European Space Agency and NASA working together to bring basically these samples back to Earth. So you can see here on the left, that's like the rover Perseverance who just landed. But then we still need a lot of more pieces to be able to return this sample on Earth. So the current concept is actually using one lander and one fetcher rover. So the fetcher rover will collect these samples from Perseverance. It will load these samples into a lander, which will have a rocket. Then we'll send these samples into the Mars atmosphere, and somehow we will collect these samples and then bring them back to Earth. That's a very ambitious mission. It will take like at least 10 to 15 years to accomplish this mission. But I'm very kind of like proud that NASA designed to partnership with ESA, and in fact, actually two of the robotic arms for the lander and for the fetcher rover will be actually built in Italy by Leonardo Aerospace. So I'm very proud that also Italy will play a big role into this mission. So the last part of my talk will be about like how can you be so successful? Like how can NASA be so successful in actually landing and operating these robots for so long? Well, my answer to that is testing and dedication of engineers. The engineers working on the test campaign for Perseverance are like a lot of people. We're talking about like hundreds of engineers working every day, sometimes even like 3 shifts per day, testing and testing and testing. We start testing from just a single screw to a single motor up to like a subsystem, and then finally the entire rover, the entire spacecraft. Is a very, very challenging and time-consuming effort. Involves so many people, and you need a lot of dedication. You cannot just do the work. You need to have passion about what you're doing, because the amount of issues that show up and come out during the whole test campaign are enormous, and you need a lot of dedication and passion to solve them. So this is actually something that I'm kind of proud of. So that's basically the reason why I got hired in the first place at JPL. I got hired to basically develop the test system for the STS. So basically for these two big robotic arms. And something that I'm very proud of is the fact that in the electronics that we're using to test this mechanism, there is actually also a little bit of Italy, in a way that we've been using Arduino to do some of the low-level functions of our basically ground support equipment. So I'm very also proud, to be able to use a little bit of Italy even in my work. And then again, relating to testing, testing doesn't end at launch. Testing continues even after launch. In fact, right now, so even when we launched Curiosity, we had a copy of Curiosity driving in the Mars yard. So Jpl, we have this place is actually, we call it the Mars yard because actually it looks like Mars in a way that has features that are very similar to what the rover will experience on the red planet. So for Curiosity, we had a rover like driving around in the Mars yard, testing some of the capabilities of the rover and how to tackle the challenges that the rover could find on Mars. And same thing we are doing for Perseverance. I actually have been involved also into the testing of the twin of Perseverance. We call him Optimism. He's kind of like a one-to-one copy of the real rover. Of course, it doesn't have an RTG, but in terms of electronics and system, it's actually a fidelity one-to-one copy. And this has been very useful, especially for the mobility team, to see how, how to tackle issues, how to diagnostic issues. And I mean, I've been very proud to be part of the team. And then at the end of this talk, we're going to have basically Stefano Capucci talking about the Mars helicopter. That's basically my perspective of why NASA decided to send a helicopter on Mars. And for me, the reason is because basically the rover didn't want to be alone, and so he needed a buddy to explore together the red planet. All right, that's basically pretty much for me. I hope I was able to give you an overview about why it's so important to go on Mars, what we're trying to achieve, and what is the future of this huge and very complex exploration of the red planet. All right, that's basically it from me. Thank you, Marco, for having me.
So thank you, Alessandro. Thank you for the amazing images about the rover. So now I give the floor to the next speaker, that is Paulo Belluta.
Hi, my name is Paulo, and a quick explanation of the title of my presentation. So a few years back, I was in Italy giving some presentations. I get to a hotel for staying during the night before my presentation the next day. The hotel, the hallway was full of people, and the receptionist was frantically waiting for the taxi cab to get all these people to the airport. And she talks to me and she asks me, "Are you the driver?" And I started laughing because yes, I am a driver, but not of a taxi. So I spent the past 15 years driving rovers on Mars. Just to give you a sense, I started driving vehicles in 2004. So at that time, in 2004, there was no Facebook, and Gmail was just born. And Skype was the new app that you had to have on your computer. And the iPhone was still 3 years away, and there were only flip phones available. And so I started driving, spiriting an opportunity on the red planet. Mars is a pretty hostile environment. First of all, it is quite big. Although it is 1/2 of Earth, the surface to explore is about the same as Earth. The landmass is pretty much the same. One complication that you have is the gravity field is about 1/3 of Earth, so it is kind of difficult to replicate the conditions under which our vehicles are moving on Mars. You can do testing on Earth, but it can get quite complicated. There is an atmosphere on Mars. Is about 1/100th of the pressure that you have on Earth. This makes it difficult not only to land on Mars, but also it makes it quite difficult to do heat transfer. So if you have the internal part of the vehicle that overheats, try to cool it off. It can get quite complicated. Also, Mars doesn't have a significant magnetic field. This means that, first of all, you cannot use a compass, but mostly it doesn't. Mars is exposed to cosmic radiation. And therefore, you need to have particular electronics to be shielded against the radiation. As a derivation of the fact that there is not a significant atmosphere, the temperature range is quite extreme. During the night, you can go down to -90, and really torrid summer day on Mars can get you to -5°C. So in order to move the vehicle, you need to be able to heat the various components so that the lubricant can work and the parts can move freely. Mars is covered by a really fine dust. To give you a sense, if you take flour is about 1,000 times bigger than in diameter than the typical dust that you have on Mars. The additional complexity is that Mars, although has a Martian day that we call Sol, that is similar to Earth, is about 40 minutes longer than Earth. And therefore, you are in a constant jet lag. You need to follow the Mars time in order to be able to communicate and operate the vehicles on Mars. As Alessandro showed you, we have landed on Mars 3 classes of vehicles. So the first one had a processor that was equivalent to a really simple microcontroller. Speaking of Opportunity that landed on Mars in 2004, and these are the vehicles that I started driving, had a processor equivalent to the Mac that was launched in 1984. And and Curiosity and Perseverance have a processor that is similar to a G3 processor. Perseverance has the advantage that has a specialized computer to do image processing, so we're going to be able to move the vehicle with added benefit of being able to analyze the terrain much quicker than we have been able to do with Spirit, Opportunity, and Curiosity. So driving vehicles on Mars is not easy. simply because Mars is difficult. Obviously there are no roads on Mars, so you just need to drive off-road all the time. And there are some particular issues that I need to deal with. There are some issues that are pretty obvious, like steep terrain, rocks, and things of that nature. But there are some other difficulties that might not be obvious to you. For example, on this type of terrain where you have a sand veneer, you get to start slipping more because the sand acts as a lubricant, if you want. Loose rocks, the same. They can slip under the wheels, and therefore your vehicle is going to be subjected to shock and slip at locations that you don't want to be. Also, it is quite important to be able to control the position of the vehicle quite accurately. Not only under these conditions, this is the image is real from Mars. So the vehicle is there just to give you a sense of the size of the crater relative to the vehicle. The vehicle determines its own position mostly by counting the motion of the wheels. We can detect the real motion, but using the cameras on board, using what is called visual odometry, that measures the amount of motion that the vehicle does by comparing the images before and after motion of the vehicle. But that is quite expensive. Perseverance, as I said, has specialized hardware to do this computation in real time. Other issues that we're going to be dealing with on Mars is, for example, there are locations where the soil type might be difficult, and it is going to be up to you to determine whether the terrain that you're going to traverse is safe for the vehicle or if it is difficult. Even though it might be flat, it might still present difficulties, like, for example, the wheels can be sinking, or they might be finding rocks underneath that are going to damage your wheels. Sorry, you may have to thread the needle. They go through really narrow passages, and therefore you need to make sure that your vehicle is going to follow exactly the path that you have specified. Also, you're going to be dealing with terrain that may be difficult. All of a sudden, there are going to be changes in the type of soil. It might be changing composition, and therefore you need to be careful and explain to the vehicle to monitor exactly the progress that it is doing, and if conditions are not met, to stop. Additional complexities that you have to deal with is that the software that you have on board, although it is quite complicated, it has some limitations. We have a pretty limited set of mobility commands. We have limited conditional expressions that we can use, and other limitations. The reason for these limitations is that before you send commands on Mars, you need to make sure that all the commands are correct. The more complex your system is, the more complex your language to explain the commands to the vehicle is, the more difficult it is to prove that the series of commands that you send to Mars is correct. as Alessandra anticipated, we are unable to use the vehicle to drive the vehicle interactively. So what we actually do is to prepare a list of commands. The list of commands include both motion commands, commands to move the arm, to use the cameras, to use the scientific instruments on board, but also and mostly commands to explain what are the envelope, the safety envelope for the mission. Therefore, for example, we specify the maximum tilt, the slope that the vehicle is allowed to drive for that particular moment, or the amount of time that the vehicle is able to use to drive, and other safety parameters to prevent, for example, the vehicle to use too much power and things of that nature. We can do simulation of these commands on the ground, but we cannot really simulate what Mars is going to throw at us. There is limited knowledge on the soil type that we're going to traverse. The only thing that we can see of Mars is basically the images that the vehicle itself is going to capture. And while there are some methods to simulate the Mars soil, these are really simple simulations that really cannot handle hundreds of meters of motion on Mars. So part of it is science, part of it is experience. So the part of science is to use the experience that we have gathered so far, is to move the vehicle as we have done for the past 15 years, but using metrics and try to find out what associated with each type of soil certain risks. One asset that we have on Mars, actually around Mars, is a telescope that is pointed at the surface of Mars. So the telescope is called the HIRIS camera, and is on board the Mars Reconnaissance Orbiter. This is a telescope that has an extremely high resolution on the surface of Mars. You can see each pixel is about 30 centimeters by 30 centimeters. And this can provide quite amazing images. For example, here you can see the Rover Opportunity, and you can also see the rover tracks under certain conditions. So using the images, the orbital images captured from the HIRIS camera, one can assess the type of terrain by measuring certain parameters, like, for example, the slope of the terrain. Whether we have rocks, try to classify the terrain according to some parameters. And just looking at the HIRIS images to determine what potential obstacles you might have to deal with. We can combine these information as layers of various difficulties in the terrain, and therefore combine this into a traversability map. Using this traversability map, we can compute what is the optimal path, the easiest path to go from one location to another location. Typically, we use two types of modality of driving. One is what we call directed driving, where we actually tell the vehicle moment by moment where it needs to go. So we specify the path exactly, and the vehicle has to follow that path exactly. This is the, if you want, the fastest method, but it will not allow you to drive past of what the vehicle is able to see from one day to the next. We have another modality that we seldom use on spatial opportunity and curiosity, simply because it is extremely slow. But it will be able to be used by Perseverance, since it has a specialized hardware on board. That is AutoNav. AutoNav basically takes pictures of the surface as it drives, analyzes the terrain, tries to find where we have geometric obstacles like rocks, ditches, ridges, this type of obstacles. And if it determines that these obstacles are too difficult for the vehicle to traverse, then it's going to find alternate routes around these obstacles. So in this case, the path is more lax. You sort of indicate where you want to go, but you're not exactly how to move around. The vehicle has some autonomy. So by combining all this, we can generate these traversability maps, where at each location we can determine what type of driving modality and what the difficulty of the terrain is. So this has been used, for example, during the landing site selection for Curiosity. This is one of the landing sites, the landing site that we selected. This is Gale Crater. But this was another landing site that we had considered that has much more difficult terrain, as you can see. It was possible to drive only at certain locations and not every location. So by combining the traversability maps and the goal of the mission that was to reach a particular location at Gale Crater, we have been able to run some simulations together with the EDL team, the entry, descent, and landing team, to determine what the risk of the mission was. So we were saying, okay, suppose that you will land at this location. What is the probability that we will be able to actually reach our science goal? Are we successful? Yes, no. How many of these landing locations are actually going to be successful in getting the mission completed? By assigning a score, one can adjust the landing site location by comparing the risk posture that you want to have, and therefore determine whether moving the landing site a little bit closer to the to your science goal is feasible or not. Other things that we can do using these quantified model for the traversability maps is to do an estimate of the duration. That is, how long is it to go from where you land to your science goal. And this was used during the prime mission of Curiosity. This is the location that we landed. This is the path that we followed, mostly followed during the prime mission to get to the science goal at the moment that we are down in this area here. So that is it for my presentation. If you have questions, you can ask them at the end.
Yes, at the end. Thank you, Paolo, for your interesting presentation. And I guess that many people would like to do your job. I think that it is a fundamental part in the mission. So now the next speaker is Stefano Capucci. I give you the word.
Thank you very much. Thank you to the Politecnico di Bari for organizing this event and giving us a chance to talk about what we're passionate about and this incredible mission. And also thank you to my colleagues for perfectly setting the stage for my presentation. My name is Stefano Capucci. I'm a thermal engineer at JPL. And for the last 4 years, for the vast majority of my time, I have been dedicated to the Mars helicopter Ingenuity. And so being a thermal engineer, my job on this project was to design and test a thermal system that would allow the helicopter to function safely and operate correctly throughout all its mission phases. But before we go too much into the details, let's take a step back, and I'm going to try to introduce you to this incredible mission for who has never heard about it, and possibly add some information for who is already familiar with it. And I'm going to try to do that by answering 3 questions. And the first one is very obvious. What is Ingenuity? Ingenuity is a technology demonstration, and it's tagging along the Mars 2020 Perseverance mission. So it's a drone, and it's the first drone that has been designed specifically to fly in the thin Martian atmosphere. We've never done powered flight on a different planet, so it's a first of its kind mission. So being a technology demonstration, its main objective is to demonstrate that we can actually achieve flight on Mars. And we want to collect valuable telemetry and data so that we can use it for future mission. And that is like the peculiar thing about the heli. It's kind of like the pathfinders for aerial vehicles on Mars. Like Pathfinder was the first rover for the following generation that you guys have seen in Alessandra's presentation and Paolo's presentation. So then let's talk about the why, which is a question that sometimes it gets skipped because we like to, as engineers, we always like to ask, how does it work? What's the design? Why did you choose this instead of that? But we should never forget why we're doing this. So in terms of imageries, we're trying to bridge in the gap between orbital images and ground level images that are taken from the rovers and from the landers. So from Paulo's presentation, you kind of now have a sense of like how much work goes into planning and the route for the rover. And, you know, it's being able to have a different perspective, like a higher perspective, definitely can bring a lot of advantages. So it gives a total different dimension to the capabilities that we have to explore the Mars surface. So what the heli is going to do, given this aerial dimension, we can scout terrains far ahead for the rovers and possible even human missions. So this is kind of like one of the advantages that you get with these aerial vehicles. So we can get where it's impossible to access some places for the rovers and for the humans, but we can do that if we can fly. So right now we have had different type of mission. We have orbiters, landers, rovers, and each and every one of these approach has their strengths and their weaknesses. And the flexibility that we can add with aerial vehicles is really incredible. And we can pair a helicopter with a rover so that we can provide efficient mobilities and scout the terrain ahead so that the rover can plan its route more efficiently. We can have independent helicopter scouts. We're talking in the 30 kilograms type of helicopter scout that is able to carry a payload, so it can be its own mission. We can have multiple helicopters for regional exploration, and really access points, and also increase the speed that we can cover and the speed at which we can explore the surface of Mars. If I'm not mistaken, and Paulo can correct me if I'm wrong, but I think MSL Curiosity has driven about 20 kilometers from 2012. And with the current model of Ingenuity, potentially, if we really push the limit, we can get to up to 500 meters per minute. So that really kind of gives an idea of the different order of magnitude of the surface that we can explore. So then, I guess let's talk about the how, which is very exciting to me. So how do we design something that can fly on Mars? How do we make something that can achieve lift? What are the particular challenges that we have to overcome? So if we go into the details, Alessandra has already talked about this extensively, but we have long distance from Earth. So what does that mean? That means the flights needs to be autonomous. So from takeoff to landing, it has to do everything on its own. And so even before we take off, we already know where we want to go and where we want to land. And it's particularly hard to fly a helicopter, because the way we figure out where we're going is we have an Nadir camera that's pointing down at the ground, and we're taking picture fast as we're moving. So we do features recognitions of the rocks that are on the surface to figure out how fast we're going and in which direction. And while we do that and we process those images, and that has to be real time, we need to control the servos and the prop motors and everything. So the processor that is on board of the helicopter is extremely powerful. We probably have a couple of order of magnitudes of power more than the Perseverance rover, but that is what we need in order to fly. Thin atmosphere, less than 1%. So the density is very low, pressure is about 800 Pascal. And so in order to generate enough lift to take off, these blades are huge for the type of weight that we're dealing with, right? The helicopter is under 2 kilograms, yet the blades are 1.2 meters in diameter, and they have to spin really fast. We spin the blades roughly at 250 RPM, and despite the blades being that big, if you hold them in your hands, they're not heavier than a sheet of paper. It's really incredible. Cold marginites. This is a challenge that I am very familiar with. So like Paulo was saying, it's very cold on Mars. You have a big excursion. You go from 0 C during the day to -90 during the night. And it's really tough to survive for the electronics and the batteries. The batteries freeze, they lose their capacity. The electronics, they crack, all the solder joints, they go bad. So you really need to try and keep everything nice and warm during the night. So we do have an active temperature control system. We have heaters on the batteries that with a thermostat cycle during the night and keep them at about -15 C. And we have multiple layers of low emissivity blankets to reduce the radiation exchange with the environment. as well as gas gaps to reduce the conduction. And the challenge here is that the rover, having the RTG, you have like two kilowatts of power to keep the rover warm. There are other challenges related to that. You need you need a pump, you need a full a thermal control system, to be able to distribute the heat. For the helicopter, we can only rely on the energy that is being produced by the solar panel and stored into the batteries during the night. That energy needs to be sufficient to survive the night, do the communications with the rover, and fly. And to give an order of magnitude, peak power for flight, it's almost half a kilowatt. So a lot of power for, even if the sky is pretty little. Anatomy of the Mars helicopter. So we have a little bit more details here. The blades are carbon fiber. The landing system is carbon fiber as well. At the very core, we have a mast that kind of runs from the bottom to the very top of the solar panel. And that is kind of like the main structure, which is also where the landing system attaches. And the landing system is springy, right? It has, at the joints, it has some spring design, so when we land, it can kind of absorb that shock, so we're tolerant to that. And it has a very wide stance, so that even if the winds are pretty strong, we don't tip over. Around the mast, inside that cube, yellow cube that you see, are the batteries, and all around are all the avionics boards, so everything that we need to do do the processing, to handle the power system and control the servos and the prop motors. So 2 counter-rotating blades. We vary the pitch of the blades with the 6 servos, total of 2 prop motors. And yeah, like we said, CO2 gas gap insulation, what does that mean? We have done a trace study that looked at aerogel to insulate as much as we could the electronics and the batteries from the outside environment. Turns out that even if you can manufacture the best aerogel that you can produce, you don't get much of an edge on the actual conductivity of CO2. And one of the benefits of being on Mars is that because of the gravity, because of the density and the viscosity of the atmosphere, there really isn't any development of convective cells if, say, the gas gap between 2 vertical surfaces is less than 5 centimeters. So that means that if you have 2 surfaces parallel to each other and the distance is less than 5 centimeters, you can assume that it's just gas conduction. So you can assume essentially that the gas is not going to start moving and increase the heat transfer coefficient. So CO2 has already pretty low conductivity, so we decided that it was worth saving the weight of the aerogel and just put a very thin sheet layer of Kapton with like low specific optical properties. The fuselage, for example, has a high absorptivity and low emissivity so that we can get as much sun as we can during the day and warm up the electronics and the batteries. And then it has a low emissivity to, during the night, reduce the radiation exchange. But, this is like a one-of-a-kind mission. So when you talk about, something like this, there's really not a textbook to look at. And so not only you have to come up with a system that is capable of accomplishing its mission, but you also have to design from the ground up the entire test campaign. And that I think that is like 50% of the job, if not even more. I'm going to start with a video here. I hope you guys can see it. This is the first early helicopter prototype testing. So what they did here is they built a prototype of the helicopter. They put it in the 25-foot chamber at JPL. They pumped down to Martian atmosphere, and then they hired a professional drone pilot and asked him, hey, can you try and fly this thing? So the professional drone pilot came in, and this is what happened. they couldn't really figure out how to achieve a stable flight. So from that moment, they decided, okay, this is definitely not going to work. We kind of have to erase the whiteboard and relearn how aerodynamics work on Mars because it's completely different. And then it starts the series of iterations and tests that we do for every space mission. And iteration after iteration, test after test, we build our first engineering development model. So we build a total of 3 helicopters, engineering model 1, engineering model 2, and the flight model. The flight model is the one that it's on Mars. So this is engineering model 1, and this was the first prototype that was able to achieve flight in the Martian atmosphere. So here comes a video. This is 2016 of the first flight that we were able to achieve. This is still in the 25-foot chamber, and we had a tether attached to the top of the helicopter that allowed to lift part of the weight of the helicopter so that we could simulate the Martian gravity. We pumped down to 800 Pascal in CO2 atmosphere, and we hovered there for a minute, 90 seconds. And this was just one, very specific test. There are a lot of other tests that needed to be performed in order to kind of like complete successfully the mission. One of these, I think it's particularly funny. I don't have any picture of it, unfortunately, but essentially we had to build a system to test wind gusts and how the servo would tolerate a wind gust, how would the servo would adjust the blades to maintain stability. What's the problem with that? The problem is that you not only have to simulate the atmosphere, you also have to simulate the wind. And we couldn't find, at the beginning, we couldn't find a series of fan or like a fan that would not overheat in such a low atmospheric density. So what we did instead was putting the helicopter on a robotic arm, and we were inside the chamber, and then we were swinging the helicopter back and forth to kind of like simulate a relative velocity on the blades for the wind. Kind of sketchy experiment, if you ask me, but the first time you do things, you kind of have to be a little creative and really try to see what else can you come up with to test your system. Aside from that, of course, we had to do all the thermal vacuum test campaign. So you can kind of see here, we're all setting up to do to simulate the Martian environment with temperature as well. So we're setting up the helicopter there to make sure that all the components do not break when they go down to cold temperature. So we cycle that several times. And so here we're attaching thermocouples, so temperature sensors on the fuselage. You can see a very focused Ben Peipenberg on the right. And we have it's called the buddy system at JPL, right? I think it's called buddy system everywhere else as well. But essentially, every time you go next to multi-million-dollar hardware, you always have to be at least 2 people, so that one is operating on the hardware and the other one is kind of keeping an eye. Hey, don't stand up right now because you're going to hit the blades, type of thing. And let me tell you, your palms are sweaty when you're moving around such expensive toys. So this is another example. Rover integrated TVAC testing campaign. So this is the full thermal vacuum test campaign of the rover integrated with the helicopter. So this was huge, huge effort, and it takes months, if not years, to prepare for this. There are over probably like 1,500 temperature sensors to monitor all components. It's a test that lasts multiple weeks, 24/7, hundreds of people involved, and everything needs to work. This was done in October 2018. But yeah, very exciting times, and we definitely had a lot of fun. Where are we now? So you can see the helicopter tucked in under the belly pan of the rover, and here we're still in Atlo, the assembly facility at JPL. So the rover is kind of like suspended on a mechanical ground support equipment, and the helicopter had just been integrated. So we are attached to a Mars helicopter deployment system, and we are just chilling on the surface right now with the rover. And the rover is looking for a good spot to drop us off so that we can spread our wings and try to fly for the first time. And the way it's going to drop us is going to be through the Mars helicopter deployment system. And I have a cool video that shows kind of like all the phases that the helicopter is going to go through when it's dropped. So first they drop a debris shield that's kind of like the black shield there, and you can see the helicopter. And then there's a sequence that fires different pyros to release the helicopter from the Mars helicopter deployment system and the rover. There's like an actuator here that puts the helicopter completely vertical. So now we're sitting vertical under the rover. Then we release the legs, and finally we fire the last pyro to being dropped on the surface. So right after we are on the surface, what happens? The rover needs to move away as fast as it can because it needs to uncover the solar panel so that we can charge the batteries. And there's going to be a few days of commissioning, which means that we're just going to stay on the surface, wiggle the servos, wiggle the wings, do a 50 RPM speed, and make sure that all our systems are working correctly. And then after that, we're going to fly. We're going to try to fly for the first time on Mars. In the meantime, the rover is going to drive away. They don't want us anywhere near him when we're trying to fly. We don't want to crash multi-million-dollar hardware on a multi-billion-dollar type of hardware. But yeah, this is coming up this spring. And lastly, I would like to thank everyone in the team that has contributed to the Mars helicopter. Like the core team is fairly small. It's probably 10-15 people, but there were hundreds of people contributing to this. Subject matter expert that at some point during this mission, during the design, came in and chipped in. And yeah, so NASA Jet Propulsion Lab, NASA Ames, AeroVironment, Langley, lots of people involved. So stay tuned, and I hope everyone is going to hold his breath with us and look for the very first flight on another planet. So thank you again. This is my last slide.
Thank you, Stefano. Thank you for your presentation. You provided a lot of details about your work, and I know that this is a quite unique event.
Thank you very much. We're very excited
to have this kind of information. So I want to thank again all the speakers because, first of all, for your availability and also for your very interesting presentations. And I think that there are many questions that one can ask regarding your presentations. So since we have a few time, because yes, we were a little bit long, but I think your presentation deserved all the time that you you took. So I want to go directly to the questions from the participants. And I know that there is a question by Lorenzo Santoro. So I give him the word.
Thank you. I am a PhD student in mechanical engineering. I think winds on Mars can be strong, carry dust, and I suppose they are probably difficult to predict. How do these aspects affect the use of helicopter scout for long-range exploration? Thank you.
That's a very good question. And actually, we do have the META instrument on the Perseverance rover, which is a weather station. And that is capable of providing wind speed, air temperature, sky temperature, ground temperature, and also the tau value, which is a value that tells us how much dust is present in the atmosphere. And so we do have a way to really know what are our boundary conditions, what's our environment. And we are right now in the process of figuring out how do the wind look like on Jezero crater, in Jezero crater. So we're trying to pick a time for flight that is not too aggressive in terms of the winds. So we can tolerate gusts up to 10 meters per second and cost a wind of up to 8 meters per second when we fly. And when we're stable on the surface, we can even tolerate dust devils. So we have a way to deal with the winds. But yeah, that was a very good question.
Thank you.
Okay. So I know that there is just another question by Marco De Tullio, because I suppose it is late for the people here in Italy. So
thank you, Maria. So thanks of all for all the presentations. I have a few questions, very simple question. One is for Cinzia. Regarding the experience of students, Italian students in US, and especially working at NASA, are there any limitations or issues related to the Italian citizenship? So since we are not US citizen, can students be employed after they work in US, or are there limitations?
There are limitations, absolutely. There are limitations to access by foreign people at JPL, period, right? Even to come and visit and to come and take a look. But this can be worked out. So there is a process that one has to go through. And ultimately, there needs to be an approval that NASA grants or does not grant. The task will have to be negotiated and approved that it is a task that does not have any kind of limitations for involvement by a foreign national student in this case. So although this means that not everything is open to foreign nationals, there is still plenty of opportunity for foreign students. And in fact, Alessandro and Stefano are just two great examples, because they did come as students from Politecnico di Torino through exactly this process of being visiting student researchers. So it's certainly doable.
Thank you, Cinzia. Then Maria, if I can, I have very small, very short technical questions for Stefano.
Yes, please.
Stefano, just two questions. The first one is, given the uncertainty on the atmosphere properties on Mars, can you tell if the numerical simulation of the flight condition has a large role in the design process, or you still rely mostly on experiments? And the second one is if there is some automatic repair mechanism or system you have on Ingenuity, just for replace something that can be broken during the release or during the mission. Thank you.
Yes, so a very good question. I think it was definitely a combination of simulations and tests. Ultimately, you need to verify that it actually works. So I think the test portion is extremely important, and it goes hand in hand with the simulations to kind of correlate your results. That is what we do also for the thermal aspect of it. But like Paulo was saying, there are a lot of conditions that is hard to replicate. And one of these was the wind. One of these is the gravity. So even if you can test your system, there's always going to be a gap, and that's your uncertainties, and that's what JPL and system engineering, that's what they're mastered at. Really evaluating that risk and quantify that risk and try to minimize it. So Håvard Grip, he's our chief pilot, and he's been working hard with simulations to figure out exactly where we can fly right now. So it's exploring the area and how long we can fly, and he's really working together with the weather team to figuring out what's the best time. But it's a lot of simulation right now. And the second question was, sorry, can you repeat the second question? What was it?
If you have some automatic repair system for the Ingenuity during the mission, something if you can, repair something that is broken, like the, several parts of the drone. Yes.
When it comes to hardware, there's very little that we can do. When it comes to software, there's something that we can do. It's a tech demo, so very aggressive. Our margins are much tinier, much smaller compared to a rover mission. We take more risk, but that's the posture of the mission itself. So we know what the risks are and we accept them. But yeah, in case something breaks, we basically have to assess if we can get away with it. But there are no ways to repair hardware.
Okay.
Thank you.
Thank you. Now we have a question by Giuseppe D'Enrico.
Hi to everyone.
Perfect.
I'm Giuseppe D'Enrico, and I'm a student of Politecnico di Bari. I have a question for you. What do you think about Starship SN10, the last prototype that it was launched 5 days ago, if I don't...
Wants to take a question? It's a tough one.
You hear me?
We do hear you. Alla, do you want to take the question?
Yeah, I'll take it. Well, we are definitely excited that the entire. So before, let me back up a little bit. So in the past, space exploration was only basically managed by these big organizations owned by the government, right? So before, the big players were mostly like NASA or ESA, and now we have seen worldwide a lot more interest from the private industry, and SpaceX is an example of that, right? So having a private company investing so much money and passion into space industry is definitely beneficial for I think for everybody. So on one hand, for example, in the case of SpaceX, right, they've been able to lower down the price of cost launch. So it means that at the end of the day, this is a business, right? So with the cost of these launches going lower and lower, it means that NASA itself, and even ESA, they will have more money to invest into instrumentation, to invest into science. So that means that, eventually, that means for us, JPL, that we more work, right? Because if it's cheaper to launch, that means we will launch more often, and then there will be more money for us, like JPL, to do cool science. And so we are definitely excited. I mean, I'm very, very happy that the private industry is also playing a big role in such a complex goal, which is like, space exploration.
Thank you.
Okay, thank you. Now there is a question by Cristoforo Battista.
Okay, thank you. Thank you, Guy, for the presentation. And my question is about what do you think about the fact related to space weather events? I think that Mars, as you were saying, has a very thin atmosphere, and I think even there is a lack of the magnetic field, if I'm not wrong. Do you protect your assets on Mars? And if yes, do you manage alerts for space weather events?
I can talk a little bit about that, and then, yeah, anyone can add. We do monitor space weather. In fact, there was I think back in December, there was a solar wind event while we were in cruise. So we were basically trying to figure out whether if we should have waited to. I'm speaking from the helicopter side of things. During cruise, we had to turn on the heli to recharge the batteries every 2 weeks. And coincidentally, the day that we had to charge, we had the solar wind event, and so we decided to wait one day to let it pass, because when you turn on your electronics and you're hit by solar wind, that's when you have damage. It's not really a concern right now that are on the surface. I'm not an expert, but that's kind of like my understanding. And in general, the electronics that we fly are, extremely radiation resistant. So we fly old piece of technologies. Like something like your iPhone would not survive the radiation environment that you have on Mars. Maybe in a few years, I don't know. But right now, even the helicopter, we're able to fly such a more powerful processor, the Snapdragon, because our mission is only 30 days. But that would not be your standard approach if you want to last multiple months or years on Mars.
Thank you very much. Very clear.
So we have another question now by Dario Pisanti. Is he connected? Dario Pisanti. Otherwise, there is a question also by Bartolomeo Fanizza.
Yes, I think the previous question is done in the chat. So, okay, I go with my question. Can you hear me?
Yes,
Okay.
we can hear you.
I was curious about to know how high was the difficulty in the beginning with because I think there's a mix of numerical simulation and experiment, and how difficult it has been to set the first to create the first set of equation to develop afterward the the method of simulation and how difficult it was to get the enough knowledge about the physical parameter to use in the experimental test also. If it's possible to have an overview of the difficult and how main problem have been solved to do this. Thank you.
I'm sorry, this
Paulo,
is with the respect of.
It depends if the question is for surface or for flight.
Yeah, exactly.
Yeah, it's more.
I think Paulo. I don't know if Paulo Belluta. Can you hear me? I think it would be nice if you can share. You know, for example, I know that you have been working on basically unlocking. I don't remember if it was a Curiosity or Spirit when it got stuck, and that's maybe a good example where you want to replicate exactly what you have on Mars, but you need to do it on Earth. So you have like a mix of simulation and real tests happening at the same time. So if you really want to talk about it, it would be great.
So regarding simulation, we have you can compute. You can use finite element methods to compute the interaction between the soil and the wheels. You need to model the single grains of sand and the rocks. So as you can imagine, the simulation can be quite complex. We have done that in really special conditions, and after days of simulation, you could generate what the vehicle does in a few seconds. So that is, if you want a demonstration that the simulation can be done, but is not practical. So in events like when we have the vehicle that has to traverse difficult terrain, we have used soil simulants. And Alessandro reminded me of terrible times in 2009 when we had the vehicle Spirit that got embedded into a crater where we had to, in order to find out what possible commands we could have used to extricate the vehicle from the soil. My colleagues and I, we mixed 5,400 pounds of clay and diatomaceous earth by hand in order to generate enough soil simulant to place the replica of Spirit, where we actually did testing for months before actually being able to command provide commands to the vehicle. So we did quite some serious testing, and I'm sure that I have some of the soil simulant in my lungs for the rest of my life.
Thank you, Paulo, for addressing that.
Yeah, that was horrible.
So thank you, Paulo. There is the last question that I have to read for Dario Pisanti, that has a problem with his microphone. And the question is for Cinzia. He asks, what are the differences in applying as visiting researcher at JPL and Caltech?
Oh, it's a completely different situation. I spoke about JPL. I cannot really represent what the rules are for Caltech. Although we are part of Caltech, we are a peculiar part of Caltech. So the university operates independently of JPL, And so they have their own student programs. What I was talking to is JPL programs. So JPL is not a university. We do not grant degrees. So we don't have students the way a university does. We offer internships to students. So periods of work study, so to speak, where a task is then performed. It's a task that provides an educational experience, but it's not part necessarily of a curriculum. It's definitely not part of a Caltech curriculum, right? If this was the question.
Thank you, Cinzia. So if the speakers agree, we have an extra question by Riccardo Basile.
Sure. If I can I ask these couple of questions? Is there still time?
Yes, please go ahead.
Okay, so thank you. I was wondering whether JPL has plans for the future in terms of power flight. I mean, before Stefano showed us some concepts which could become reality in the future, probably depending on the success of this power flight that will be performed. But I was wondering if there was basically a team of people right now who are already thinking about early phases study of missions of that kind, exploiting multiple drones, probably working alongside the rover, for example, just like Perseverance, but in a more complex scenario. And also I was wondering what kind of restrictions there were for students before Cinzia named a few. I think, correct me if I'm wrong, that those restrictions are basically related to ITAR. And when you mean that there are, when you said that there are workarounds, do you mean that basically those ITAR restrictions get lifted from you, for you, or that you simply can work at JPL but on subjects, on projects which are not affected by ITAR? I was wondering whether you could clarify a bit about this. Thank you.
Sure, I'll try. In saying, if I did say workaround, I definitely did not imply the type of workaround where you are doing something that you should not be doing, right? What I did say is that there is a process, and the process involves defining a task. And for a student on an internship program, I would think that the advisors would look very, very seriously at tasks that do not have restrictions. And the restrictions do come from ITAR. You are correct. So if there is the necessity to have access to information that might be ITAR controlled, then we do have a process. And the process can be that of waiving such restrictions or producing some kind of understanding, right? And this understanding is worked out in a document, and it has to be, of course, approved. So that's what I meant by process. Depending on the situation, it might be possible for a foreign national to have this kind of access through the process of waivers, or what is called a TAA, which is really a technical authorization. So it's an agreement that there is going to be some information that is shared. And of course, it does have its requirements and limitations. Regarding your first question, well, that I happen to know because of my job as Associate Chief Scientist that has a role in the JPL internal research and development programs, that's definitely a subject of research to look at systems of aerial mobility for Mars and for other targets in the solar system. So it's, I would say, in the research phase, there are some ideas. Of course, what is being considered is there a science case? Are there questions that can be optimally addressed by having a system of helicopters or some other aerial vehicles? Typically, for ideas to become flight projects, there needs to be a scientific driver that sort of justifies what need to be built and deployed. And I can tell you that there is definitely ideas being formulated in the research groups at work to identify what these drivers might be.
Thank you again. So there are many other questions. I suggest to the participants to contact directly the speakers by looking for their contacts that they can find. But we give space just to the last question by Marco Núñez.
Thank you. Can you hear me?
Yes.
Okay, I have a different kind of question. I ask, due to COVID restrictions, if now you are all working is smart working basically, because my idea is if someone has to apply now for a visiting period at JPL, is he allowed to stay there or should he work from a house in US? Thank you for the answer.
Right now, there are no internships that are offered physically, right? As a matter of fact, activities that are non-flight projects are extremely restricted. I cannot go to JPL, so I have to do all of my work remotely. And so do 5,000 people. And the internship program at the moment is done remotely for US students only. And this is the plan in place for the next several months. So what we call the summer cycle, which typically covers from June through the end of August, is remote only. We would not have the opportunity to enroll foreign students in remote internships, because it does require a process of vetting anyway. In other words, a process of visa request to access the laboratory, even logically, having a computer accessible and linking to the IT network of JPL. So at the moment, they are not possible. You just couldn't apply today. But let's be positive and look to the future, to a time when we will return to work in person, and think about what opportunities might be there. I would recommend that you explore and get to know some of the people who might be willing to host you in future collaboration.
So thank you, Cinzia. I think we can close the discussion. And I want to close with a curiosity, because when I was at JPL, they tell me, I noted in one of the pictures that Alessandro showed that there was a signature JPL on the wheels of the rover. And I know that JPL was proud to leave its signature in the space, because where you don't have atmosphere, the signature remains on the terrain after much time. And I know that then they decided to remove this signature because NASA was a genius. And I want to know if you confirm this story and if you know this story. Some of you.
I would like to address that. So, you're right. So for curiosity, on the wheels we had actually a kind of a Morse code saying JPL, right? So as soon as NASA discovered that, they said, well, no JPL logo on the robot. So then for the new mission, as I showed in my previous presentation, JPL has been able to put, let's say, a second Easter egg. So this time was the first time we had, as shown, the recording of the landing. So we were able to see basically the real parachute opening on Mars. And there, even though we are not being able to put the JPL logo, we have been able to put a motto, like a sentence that's very, it really kind of like really represents JPL, which is their mighty things. So it actually, in the most kind of like, I think it was like ASCII code in the pattern of the parachute, that was actually saying their mighty things. So these have been like a new Easter egg that JPL has been able to provide to kind of put like our logo in the mission, even though we are not officially allowed by contract to do so.
Yeah.
So I don't know if there is anything on the helicopter that I'm. Stefano, do you know if there's anything peculiar on the helicopter that we will discover in the future?
Not that I know of.
Okay, I'm very curious. I'm quite sure eventually something will pop up and it will be like JPL or something. No, I don't know. I'm joking.
So thank you for all the presentations, and now we have to close, and I give the final word to Marco. So I want to thank Alessandro for organizing the event from JPL side, and Marco for organizing the event. So thank you.
Thank you, Maria. So Cinzia, Alessandro, Paolo, and Stefano, I really want to thank you for this very inspiring seminar on a truly topical theme, so a hot theme for the moment. We also thank you for your work in advancing the science on a very frontier topic. So I'm sure we will see some good news in the next weeks from Mars, so we will wait for that. Of course, we will work hard to promote as much as possible the collaboration with JPL. Let's say we can think to be dwarfs standing on the shoulders of giants from our side. So thank you for everything. Please let me ask this the courtesy to answer the possible PhD students or colleagues questions that could contact you. They could contact you. Please ask them, because we have to cut since we are discussing for about 2 hours, so it could be a lot also for you that are very kind, but 2 hours are enough. And I really thank you so much, and thank everybody for participating. Thank you.
Thank you
very much.
It was a pleasure.
Our pleasure.
Hope to see you soon in person.
Yes. Thank you.
Bye-bye.
Bye-bye.